All right, so welcome everybody. This is Flow Seminar, where Flow stands for Federated Learning One Word Seminar that was created to provide a global online forum for the dissemination of the latest scientific research results in all aspects of federated learning. And today is my great pleasure to host Nick Lane, who is currently a professor at the Department of Computer Science and Technology at the University of Cambridge, where he leads the Cambridge Machine Learning System Labs. And also, alongside his academic roles, he's also the co-founder and chief scientific officer of Flower Labs. And today, he's going to tell us a bit more about why the future of LLMs and AI in general is federated. So thank you, Nick. It's a great pleasure to have you for a second time at Flow, and floor is yours.
Great. Well, thanks so much. I really appreciate the invitation. And what I really love about this invitation is that it's great to give a talk where you're speaking straight to the community who are looking at these topics. What I wanted to do today was actually make this a fairly casual talk. I wanted to tell you about some of our thinking about where we can take federated learning next, and why we think it can play an even larger role than it has in the past within sort of the mainstream movement within foundation models and large language models, and how it can have this sort of prominent role, we think, in where we're going next with AI just more broadly. And before I get to sort of the technical parts of the talk and sort of unpacking what I mean by this, I first just want to fully acknowledge that the thinking and the core work I'm presenting today is actually the output of many different people at the Cambridge Machine Learning Systems Lab and at Flower. And so there's a number of papers here that has sort of influenced my thinking and kind of led me to present the sort of ideas I'm expressing today. And so I just want to fully acknowledge all of these the folks here that you see pictured from the two organizations, and also these series of papers that underpin sort of the ideas I'm expressing today. And my aim is actually not to dive into the details of these papers. I think they would be better served. Like each of these papers would make it, fantastic, half talk. But what I want to do is just sort of express the underpinning ideas, and then show you how these pieces of work fit together and sort of advance where we're going with federated learning more generally. And so just to sort of transition here, the exciting opportunity that federated learning can play, I believe, is largely driven by the fact that we have now sort of reached a point where we kind of see a clear recipe for moving AI forward. And so it's unclear how long this recipe will persist. It's unclear how long the types of techniques we've developed will continue to respond to the injection of compute and data. As far as I can see, we haven't reached the limit yet. And so what that means is that one, not the only one, but one of the clear directions that we can use to scale up AI and make it more capable is by building systems that are able to digest larger and larger amounts of data and are able to bring to bear more and more compute. And so we believe that moving forward, federated learning can play a central, maybe even a pivotal role in us being able to do this. And so for that reason, since about November last year, we've been working very hard to explore one sort of vertical of this, which is how you can use LLMs. And we've selected in particular the pre-training of LLMs, so not the fine-tuning or other types of possible directions that one might take. We were just going straight for the sort of more difficult task of pre-training an LLM, where you're constructing it from scratch using the available data that's accessible under federated learning. And so we showed, for example, in March 14th, that it was possible to train a 1.3 billion parameter LLM. And that was actually a big deal for me personally, because I've talked to a lot of folks, and the strong message I got from many of them when they heard the word federated learning was that they perceived it as a technology that would only be applicable for relatively small models, perhaps when the data is highly privacy sensitive, but they found it to be, they believed at least, it wouldn't be a technique that could scale in this way and that could scale in this direction and participate in this avenue of building large models. And so we were really happy when we were able to build a system that could demonstrate that 1.3 billion parameters was possible using GPUs that were distributed around the globe. And then so we followed it up with some work in July, a few months later, that showed you can build up to a 3 billion parameter model. And so when I saw this flow invitation, I was wondering what can we show you folks that we haven't shown before? And so today, in October 9th, we thought it was a great time to show you what we've been working on next in this general direction of travel. And so I'm really delighted to announce that today we're going to show you live during this talk our capability of pre-training a 7 billion parameter model. And this is really, I think, an important milestone because it now shows that with federated learning, you can cover that whole sweet spot of between 1 to 7 billion parameter models where you have enough parameters to do some serious damage. You can really have models that can perform quite, well, almost incredible capabilities depending on your perspective. And yet we can arrive at these models with federated learning. And so I've done many talks and I've done a lot of research into different areas over the years. But one thing I've never tried to do was do a remote talk with a live demo involving 4 other people. But that's what we're going to try to do during this talk. So let's take a step back and we're going to show you the system we've created and give you a taste of the fact that we can actually do this. So let me stop sharing. I want to introduce 4 other collaborators here. There's Pan Hang in the room. There's Javier Fernandez Marquez. There is Alex Aikab, and then there's Lorenzo Sani. So if they just want to just turn on their cameras for us. I'm just looking for Alex. And so what we're going to do is we've got these 4 folks, Pan, Alex, and Javier are going to be manning nodes that are based in North Texas, Utah, and Central Texas. We're using just a cloud provider that allows you to target different locations. And so we are going to, during the course of this talk, advance this 7 billion parameter model a few steps forward while I'm giving this talk. And so our first, we have Javier and Pan. They work for Flower. Javier is a lead research scientist. Pan is a research scientist. We have Alex and Lorenzo. They're PhD students at Cambridge, but they also work for Flower, providing us with some really great bits of technology too. Maybe if I hand over to Javier, you're one of the guys who are going to be running the client node of this experiment, this live demonstration. Maybe just tell us a little bit about what you're going to be doing, what hardware you're using in this experiment.
Yes, is it okay if I share my screen briefly?
Yes, sure.
Yeah, sure. Well, I'll just share my whole screen. If I can figure it out. Oh, here. Yeah, so I'm in charge of keeping an eye on a machine that has 8 H100s. This acts as a client, and probably if you have been using Flower recently, clients we now call them super nodes. These are, can be a server, it can be anything that is constantly pinging the server side, that we call it the super link, for new messages that have to be processed in this node. And this node has 8 H100s. We are now in the middle of a communication round, so you will see some action happening here. And the moment the model completes being the communication, which is a 7 billion parameter model, local training will start. In this node, I have a portion of the pile dataset, which is roughly 300 gigabytes uncompressed. And I think other folks have similar setups.
Great. And then so we'll be running a conventional FL topology for this particular experiment. And so the aggregation node is going to be manned by Lorenzo. He'll show us a little bit more about this setup, and we'll see this training curve evolve during this talk. So over to you, Lorenzo.
Hello, can you hear me well?
Yes, sounds good.
So yeah, as Nick said, I will be handling the server side of things. So the central parameter server that is responsible for the aggregation and the orchestration of the entire federated learning. Now, as I was saying, we got a bit lucky. We are in the middle of a communication round, so there's not much happening on the GPU side of things. But maybe I can show some logs of what's happening for the server. So let me check if I can share the screen. Yeah, I found the button. Share the screen. Okay, I think you're seeing the screen, right?
Yeah.
So here, what I'm showing you is 3 types of logs. We have on the top, what is superlink logs to for our experiment is basically ending the messages between the server and the super nodes available. In the middle, we have the server that is actually it's just uploaded a communication message, as you can see down here. And at the bottom, we have another super node, like a client app, as the one that Javier had. So hopefully, later we can show you some cool convergence curves regarding this this training that is currently happening. And yeah.
Great. So this is an unusual way to start a talk, but essentially we're going to start this experiment at the start of the talk. Yeah, Pan, Javier, Alex, they're all operating these nodes that are these H100 nodes that happen to be in 3 different parts of North America. We have another node in Cambridge. They're all connected by regular wide area links. So, 100 megabit per second style links, far cry from InfiniBand and all the things you might find in a data center. But the real message here is that while most of the time you give technical talks and you sort of have like this, it's a figure from a paper, we're trying to drill home the fact that doing this is possible. You can use federated learning to train models of this size. And in fact, we're doing it constantly because it's sort of really a green area of research. I think switching from this dimension of being sort of, very privacy focused for federated learning to one where you're considering a much wider array of workloads presents a lot of opportunities to kind of figure out how we're going to design these systems, how they're going to be optimized and so on. But you can build the basic system today. And then you can show how FL can be, as I'll argue the rest of this talk, pivotal, absolutely pivotal if we're ever going to reach the types of outcomes that people are subscribing to AI right now. And so we'll come back to Lorenzo in particular and just see if we're successful, taking a bit of risk here, but that's fine. Let me go back to the slides. We'll come back to Lorenzo later. So as you would have gathered, the main aim here is to try to ride this wave of providing more capable AI by applying and making available more compute and more data. And one of our main reasons for trying to do this with FL is that even though this sort of recipe, this sort of opportunity hasn't been around with us for that long, we're already starting to see signs that, we might be running out of data, we might be running out of compute. And so there are papers such as this one I'm highlighting here that are indicating potentially the amount of data that is available conventionally. So that is the amount of data that's available from the web, from the internet, that can be used when you're training centrally, is potentially starting to run out. And so then if we have this opportunity to improve AI through using more data and accessing more compute, if the centralized directions are starting to run out of this resource, if we look towards FL, I believe we're going to find the availability of much more compute and data. And so the underlying thesis of everything I'm talking about today is that if we're running out of these two key resources, I believe federated learning may prove to be a key answer in this. And so while I'll be using the word federated learning and the techniques that we're showing right now are obviously federated learning based, I think in the long run, we're going to see the techniques evolve a long way. And so you could replace this word federated with decentralized, with other sort of more exotic forms. But the main point here is that the direction of travel that we believe that systems of this kind need to be built is one where that the data and the compute are not housed all in one place, but it's a system in which you're enabling the composition of these resources, even when they're connected from sort of very conventional types of communication links, rather than the specific ones that you find in data centers. And then this would be a complete change, a complete game changer in terms of how we think about federated learning, which is hence the title. Up until now, federated learning, which we all know and love, we've been using it to great success in many settings where there's no other machine learning direction that it's applicable. So for example, in hospitals with private data, in industries where there's heavily regulated data about how it can move across borders, in systems such as robots, where there's a big win if you can build your models in a more continuous and open world fashion so they can adapt to the complexity of the real world, rather than the sort of the shortcomings of the data sets they have available. It's a marvelous solution, but what it lacks is extreme relevance for many of the breakthrough systems that you've heard of and is often driving the narrative of AI. So if you look at things like AlphaGo, if you're looking at new systems like ChatGPT, none of these systems are being trained using federated learning, but we think that might change quite soon. And so one way to think about this and sort of break it down is into two types of opportunity. The data opportunity, which I've loosely been referring to right now, up until this point. And the way I want to frame it for you is that it's common to talk about the data that we're training on right now, even for the largest types of transformers, where you're really harvesting all the data from the web and the internet, to an approximation. It's common to talk about this data as being enormous, and it certainly is big in historical terms, in terms of the scale of data that we've trained in previous years in the machine learning field. But it's important to realize that it is only a tiny fraction of the data that's available in the world. And so what we believe is that there is a lot of data that's available, that's distributed, that's sensitive. Some of it's private, but some of it's not. Some of it's just difficult to access. And so, for example, recently I was talking to a company called Samstra, I think is how they refer to their name. And so they build dash cams that they're deployed quite widely in the US and the rest of the world. And what they were describing was that these dash cams process just as much data every day as YouTube does. And so while we think of YouTube as this huge resource that's available for building models of this kind that you can access because it's internet available, there exists, you can find, a company that is certainly successful, but not a household name yet, that has actually got the equivalent amount of data as YouTube, but it exists on the edge in these dash cams. There's computation available to it, there's network available to it, and that's an example of data that will never find its way into the models that we're training. And of course, there's obvious examples that you can think of yourself, such as the data on smartphones, the data in enterprise laptops. And again, the usual suspects such as regulated data that might be in government offices, factories, where the data is just difficult to access, similar to these dash cams. And so there's only one way, I believe, you can scalably access a large fraction of that data, and that is by developing the systems that we all know already. Federated, distributed styles of machine learning pipelines where the data doesn't have to move. So that's a big opportunity for building these big models that is in the direction of data. The other direction I think is important to think of is compute. And so one way to think of the compute opportunities that exist when we start to use decentralized methods is that if we just start to look at some really strong examples that exist. And so here is the number of flops that exist when you assemble in one data center 22,000 H100s. And it sort of totals up to around 2.9 exaflops, which sounds like a lot. But my point here is that if we compare to other collections of compute that are available, we start to see that it is not nearly as much as you might think. And so one example of this would be if we just look at all the Snapdragon phones that were sold in 1 year by one company, this happens to be Samsung, and we look at all the flops that are available, and this is not all the phones they sold. This is just one category of phone. It happens to be their high-end Galaxy class from a couple of years ago, ignoring the lower end and mid-tier phones and all the IoT devices and everything else that Samsung obviously sells. But if you just compare these two numbers, you can see there is a huge vacuum of compute that is never going to be utilized by centralized methods, but can be utilized with decentralized and federated means. So the key question is, can we develop technologies, methods, and overcome the challenges that are obviously going to be there that could tap in to populations of compute that is currently underutilized and frankly just completely ignored by machine learning. And so this is just one example. I'm not saying we have to train LLMs on phones necessarily, but I'm just pointing out a very relatable example. I could have, picked a particular family of laptops that are underutilized, or a particular family of, the compute that happens to be in a class of car, or in regular factory machines that are commonly deployed. All of that compute is ignored when you go down the path of centralized only ML training solutions. And so the underpinning thing I want to suggest, and I really want to kind of get people's feedback and discuss with you, rather than kind of deep dive into sort of the technical nitty-gritty of some of the papers we've been making, is that I want to ask the community, is it time that we expand our view of what Federated can do and start to ask ourselves if we can make all of AI infrastructure that services the training of all models of all varieties and shapes, but doing so with decentralized forms of infrastructure. And so there would be a lot of, I think, important improvements and capabilities that such infrastructure could afford us that go beyond just accessing more compute and more data. And so some of those are listed here, such as if we can have true combinations of compute being able to be ad hocly combined to train, for example, a one-off big model, then you can have true partnerships between organizations. Or in that sort of topology, there's real control over data that's being used and where it should be used and not be used. It's also, I really feel this is an important factor, that it becomes a much easier job of sharing resources. We don't need to make a huge data center for every huge next step of a model. What we can do is have folks, and when I mean folks, I'm talking about big organizations. So big organizations sharing resources temporarily to have greater utilization of our global pool of data and compute. And so that's a path forward if we can solve technical challenges that make decentralized, federated kinds of infrastructure that are general purpose possible. And I'm talking to people who are intimately involved in this space, and so you'd obviously start to realize there are some serious challenges in building these systems. Not only the obvious ones such as efficiency and how do you get these models to converge as well as they do in a centralized setting and so on, but the sort of list goes on really of challenges that exist, but when you start to look at this type of opportunity, they are quite substantially different from the ones that we commonly study in our FL papers, which is one thing I want to advocate for us to start to think about these other types of challenges that exist when you use federated style techniques in this sort of direction. And so when we started this journey back in November, we're actually getting our hands dirty and building these systems, I thought it would take quite a long time. I never thought that by October the next year, we could easily, and we're doing this all the time, we can easily train, 7, 10 very large LLM models using federated learning as we explore the different design spaces that are there. We're doing it very easily now. And so we're obviously quite skilled in this space, but there's no difference, I think, in what other folks are going to be able to do if they start to lean into this heavily and build similar types of systems. It's a smart community out there. And so for that reason, because we've been able to go so far in such a short distance, I think the potential of this direction is even brighter than I originally thought. And so what I've started to say is that I think because we can move so fast and we're able to make so much progress in such a short amount of time, if communities like federated learning start to lean into the study and the development of methods of this kind, it's extremely likely that in the near future, every state-of-the-art AI model will be trained using federated learning. And that's not to say that they wouldn't use some type of centralized, capability or resources in their training mixture and in the way they function. But the star of the show, the most important techniques, the things that really drive that model towards being SOTA, I believe will be federated learning. And for that reason, some of those other techniques that might exist in centralized might start to diminish in importance. And we'd basically say these models are trained using federated learning and like, very similar techniques that come subsequently. And the main reason I would point to is the data and compute opportunities, although the societal style of benefits, I think, are also really prominent. Let me tell you a little bit about the systems we've been building. I want to sort of move through this sort of fairly quickly, but we've got technical papers on all of it, and source code will be available very shortly. I want to just describe primarily 3 papers just very briefly. The first paper we call Photon. And so this is sort of the original paper that we've released here, where we try to lay out this argument for why federated learning can be such a needle shifter in the direction of enabling large-scale models. And so Photon is an experimental system that enables us to examine the design space of how you can build both federated systems and also start to bring in some of the techniques that you might see in a data center, but apply them to infrastructure that happens to be working globally, where some of the links are extremely slow, comparatively speaking. There's an algorithm there that enables us to drive this system and have really good convergence and so on. But the big picture you should think of that Photon is enabling us to do is a system that's flexible enough that combines both the ideas of federated learning and the ideas that are common within distributed training as it exists within data centers that we can use to understand how we can build models of this kind. And so we've been running many experiments. If I just show you a conceptual picture here, we've been running many experiments where you can have data and compute in different physical locations. Unlike typical federated learning, we enable certain configurations where the data might need to move to a certain compute region, so you can do things such as optimize wall clock time of that system, of that training run. But then it's entirely possible to decide that certain data has to stay with the compute where it's local to it as well. So you can maintain those privacy benefits too, if necessary. But the underpinning sort of drive here is that through the easy combining of compute and data around the world, you can arrive at LLMs in this case that are just fundamentally more democratic because they can be assembly of a lot of different folks working together. But moreover than that, they can become LLMs that are much stronger, that can be trained than centralized systems as you sort of advance and push the advantages of federated learning even further. So going back to the details of Photon, you can see from this architecture diagram here, we have separated nodes that provide data from nodes that provide compute. And then we have one or more aggregators that can combine the data under a usual federated learning type of approach. As I was mentioning before, the design principles of this system are include the separation of data and compute, but it also includes some real heavy lifting on the node side in terms of allowing the local nodes to train efficiently those local training epochs on LLMs in particular. It includes capabilities of allowing the compute that's available on each node to be used optimally and to have the sort of outer loop topology based on the needs of the training run. So whether it's private or not, or whether it's best to run in a ring topology or not. And so what it is really is quite a unique system that bridges these two worlds of ideas. People were building federated systems that sort of exclusively might have a central or perhaps a decentralized aggregator in them, but there wasn't really a type of framework that could simultaneously allow you to inject into them things that were kind of quite standard in distributed training in centralized fashions, such as Photon also allows you to use a ring topology when you're doing the exchange of the gradients between the compute nodes. And so this illustration here shows you an example where data is streaming in to nodes that are doing compute. The nodes that are doing compute are then using a ring topology to minimize the communication costs as they're converging on a global model that trains for the data that's available. And all of this is built on top of flowers, so then people can sort of build different variations on this theme. One interesting, there are many, like any system, there are a lot of moving parts. One thing that I also want to highlight just with an illustration, just as a one-off anecdote, was that we found when you start to deploy Photon in different configurations of system, we've been doing this where you get a realistic set of hardware that one might want to kind of combine the compute of in order to train a large model. And then sometimes those nodes might be strongly connected, meaning that they're combined, that they're linked together with something like NVIDIA-Link. And in those cases, what Photon does is makes a decision in terms of what should be the node level communication topology that's used. If it detects that there's a lot of compute available, it drops into sort of like a typical data center style of training and using those GPUs, where you might be using something like FSDP and some sort of policy like 0. So you're really maximizing the high-speed links that exist between the GPUs. But what it's also able to do that you can't find in other systems is that if you deploy it onto a node, and this could be multiple nodes in the same network of training, where that node might be a weakly connected series of GPUs, perhaps they're using some sort of PCI bus, then it'll make a decision to make in these individual GPUs work together almost as a micro federation, where the local work of the GPUs is happening. There is very limited amounts of communication happening between these GPUs because the connections are just so slow, and it makes that sort of decision. And so there's a lot of different of these sort of system level optimizations and also optimizer level optimizations that we've done in this system. But I just wanted to sort of just show you one example, just in this sort of given the amount of time we have available. If I show you some of the results we've arrived at so far, let me just show you what I think, given the time, I can show you just the training curve of the 7 billion model that we've started to train for the last few months now, and on and off as we experiment with what's it like to get good performance out of training models at this scale. And so this is an actual experiment that we've done much before this actual live experiment that's happening right now while I give this talk, where we use the C4 dataset, 4 different locations, each location having H100s. And what's important here is that the quality of model, and so you can see that the global model validation and global model train, they're arrived at by federated learning. And so you can see, as measured by perplexity, the federated models are certainly no worse and are actually ahead of the centralized ones. So there's what these show us, and what our other metrics that I could show you indicate to us that the quality of these models that are being trained by federated learning are no worse than those of centralized. And we can clearly state that now, which is an important part. You are not losing anything in model quality when you train in this way. There's no penalty in training in a federated manner versus centralized in the context of the types of models that result, which is an important factor. We've also started to discover a lot of opportunities to make the system even better. And so let me just quickly run through a couple of these explorations in terms of the types of techniques that can evolve out of this thinking. And so this is a very new paper that we only finished last week. The kind of technique name is depth. The idea is that we discovered that it made sense to have unique embeddings that were specific to the clients. When you're training in a centralized manner, as is shown in this illustration here, you have your transformer and you have your embedding, which is illustrated here in the middle. You've your transformer bottle, your transformer body, and your embedding layer. And then these embeddings, typically in a centralized case, are uniform across all the data sets that might be combined. And that's because you have time and opportunity to massage that data and come up with one single embedding that represents that data that you have available. What we realized as we started to build systems of this kind was that there was huge mileage available if you allow the training to occur where the embeddings are specific to the data that's available at the clients or the nodes. And so what depth enables to be possible is something much more like this. And so this is actually illustrating on the left-hand side the original design that you'd find in a centralized case, but you also can deploy in a federated case where you have the same embeddings across all nodes. And then there's 2 variations here that this paper examines that lead to better performance in federated settings of training language models. And so what TRIM does is a partial decoupling of this design, and where the spec is the full-blown version of it, we've actually included not just the embeddings, but positional coding and everything else that's required. So by doing this, by allowing the embeddings to be specific to the data that's actually at each location, and you haven't got one size fits all embedding that's consistent across all the nodes, which can be incredibly wasteful, we can see huge gains in training federated models of this kind. And so let me just show you a couple of the results that are possible when you are using the kind of designs that I talked about in Photon, when you combine them with these ideas from depth. And so for one thing, we found it's totally possible to train models of equal quality, but where you have embedding counts that are reduced by 80% or more when you're training at scales of 1 billion. There are also obviously going to be strong reductions in communication costs. And so at the greater than 1 billion scale, for this particular technique compared to the vanilla sort of shared embedding across all nodes, we have reductions on the order of more than 600-fold in terms of communication costs. Importantly, what's being shown at the bottom here, where we've done these experiments in a multilingual and a sort of a multitask kind of environment, there is no loss in the actual quality of the resultant model. And so there is, even though you reduce the number of parameters, because those embeddings correspond to the data that's available each place, when you apply the types of training methods that allow this to work, we're actually able to produce models that have all these benefits, but that are certainly no worse than the conventional models at all. And in fact, I could make some stronger claims here, but for the sake of time and the fact that I have to walk you through some of the logic here, I'll leave it just at this sort of efficiency argument. But we think there's strong reason to think that federated style training could even result in better forms of utilization, particularly of data that has a lot of a heterogeneity within it, which is going to be a natural outcome as you scale up the size of the data that you use. Let me just highlight something else that we've been experimenting with. Again, very just briefly, it's a different paper here. It's a technique called World LM. And the idea here is that we're inspired by a lot of the existing work in the community that is considered how you can inject hierarchy into your federated networks in order to train a better model. And so while there's a complete approach here that I'm not going to be able to cover, the main reason for us to study what would it look like if you are doing pre-training at this sort of global scale using federated learning, our main motivation is that we expect, in terms of real use cases, organizations will have quite significantly different requirements on how they function. So you can think of different participants within a federated network having different requirements in terms of legal, privacy, security, and so forth. They could be sharply different. And what we want to enable here is that the system doesn't have to default to the most severe settings, the most restrictive settings of any one single participant within it. And the way we achieve this is by using a style of hierarchical learning, where we also allow the migration of data that is highly similar between these nodes when it makes sense. And so the way that we make this determination when some parts of data, if it's sufficiently not private, can move between the nodes in terms of when it's being trained, is that we have an attention mechanism that's able to make this decision. But the key sort of next step of this method beyond that of Photon is that it enables federations of federations. So the federations of these different organizations can now be possible with sharply different characteristics, and that the overall behavior of the system does not default to any one of those characteristics of those federations being forcibly applied to everyone else. And so one of the places where you can see this come up is when you apply it to differential privacy. I'm just going to show you a very quick result here. We don't believe that this is the complete answer in being able to support under this pre-training regime using federated learning, the capability of differential privacy. But what we've discovered is that is in the kind of basic Photon system, differential privacy is a non-starter. What we do under World LM, where you can start to have a differentiation between these sort of silos or federations working together, and because the fact that you can train in a way that a setting doesn't have to be applied to all different parts of the network, is that you can have quite big jumps in the quality of models that result even as you apply federated learning. And so one example sort of result being highlighted here is that the perplexity of a particular sort of model setup here, when you apply federated learning, balloons out to be more than 700 under conventional federated learning when you look at this example happen here. But then when we apply this World LM approach on top of this basic setting, you can see that the perplexity drops from 700 all the way back to 100, which is, in shooting distance and sort of like in, it starts to become more comparable to the types of perplexity that you would see from just regular data when you're training it. So here's an example with FL getting a perplexity of 107 on a similar sort of data set. So that's just sort of a snapshot of the types of methods that we're trying to enable. I'm conscious of time. So what I want to just do now is just start to wrap this talk up, and we can take a few questions. We can start to argue whether this is a great direction or not for FL to go. But just sort of start to unwind, the big idea here is that we can take FL beyond where it's been and have it become applicable not only in key scenarios where privacy perhaps is a big concern, have it applied not only in cases where there's heavily regulated data, but have it applied in the mainstream direction of AI, which is all about how do we scale these models up, at least for a big chunk of the AI community. Federated learning can apply and can be a key enabler for us to go in that direction, we believe. And so the big announcement we had at this talk today is an announcement that we can easily train 7 billion parameter LLM models pre-trained with federated learning now with the methods that we've been developing. And we invite everyone else to dive into this direction with us and discover the problems that exist there. So now I'm going to hopefully return to the demo that we started this talk off with. And so Lorenzo, if you're still there, perhaps you can give us some good news. And did we succeed? Did it work?
Yeah. We've been training a couple of clients, and yeah, expect the results. This is one of the experiments we try quite often.
Can you show us something here?
Yeah,
about...
let me show some metrics. If let me try.
You can briefly show us something, that would be
Yeah.
amazing.
So let me try to share this part. Can you see the screen?
Yes. Is this the okay?
Okay, for example, this is the metrics we are collecting from one client specifically that is currently training. And as you can see, we are collecting a lot of stuff like stuff related to activation, so L2 norms of the models, but also like more concrete metrics such as cross entropy, token accuracy, or language perplexity.
And so what should
And
we help us out here? What should we be looking at?
sorry, say it again.
Sure. Which of these figures tells us an interesting story then?
Oh yeah, well, I think the most important things regarding this local metrics is that they look very different from what you can see from the federated side of things, from the server side. So especially since we can do this type of experimentation and we have during experimentation the control over the clients, so it's useful to get insights about what's happening locally, especially from the machine learning side of things. For example, the screen that I'm showing you right now, you can see that these three metrics are all related to the specific task that the client is training on, so language modeling. And as you can see at the beginning is not performing very well because the global model needs to adapt quickly to the client distribution, the specific distribution that the client has. This is particularly relevant for the datasets we're training on with this experiment because the pile dataset is very highly heterogeneous. But what we can show here and in many other experiments that you can find in the paper as well, is that bigger models, for example, these of 7 billion, can really adapt very quickly when it comes back to the client. And the client can put in a lot of information as soon as it received the model update.
I see. And then so these curves were partially completed while the talk was going on, I guess.
Yeah. I was open to see something moving, but like delay network, we can try maybe to update the page, but not likely that will change something. Let me see. Yeah, it's it takes some time to train some steps and to update the new metrics to, well, maybe you recognize this, the weights and biases. So yeah.
Sure. Okay, great. Well then let's land this plane and I will just wrap up and we can take a few questions. So that's just to say that these style of models we think offer sort of a new category in foundation models in that they have access to types of data, sort of varieties, categories of data that would be otherwise not available to the ones that you see below here. So these are sort of a federated foundation models, federated LLMs in this particular case. And so today we completed the set and going now from 1.3 to 7. This is something that the software we have can do easily. And so we're just always looking for ways that we can improve different characteristics of this training to make it more useful. So our sort of next step, a logical next step would be to sort of show these models at even larger scales, and to connect the dots whereby we think that these models can start to even outperform those of centralized models as we start to improve the data and the types of training that are available and their ability to handle heterogeneity in those data sets as they scale, which would be an enormous deal if we can show those sort of results. And then in my final thoughts would be just that I think it is important for us as a community to start to think about different settings under which we want to target our FL systems. I think, for example, an interesting setting that is seldom or maybe never thought of is how would you combine 3 or 4 small data centers together and train a large model? How would you, for example, or take enable a scenario that is more like SETI at home, where people contributing not tiny necessarily devices, but single GPUs, 2 or 3 GPUs from their home together to build a large federation? What would happen if a fraction of that data is private? What happens when all of it's private? What happens when there's a mixture? What mixtures matter? There's a lot of settings for us to consider and to digest. What are the key ones we want to make as cornerstone scenarios that we want to build federated methods for. And alongside this, if we ever want these techniques to be developed mainstream, not only do we need to find ways of making them scale, we need to be able to do a couple of things at least, if not more. One being enable the sort of the tuning and the types of ML ops that are so common, that are just sort of taken for granted and centralized. We need to find methods of those kinds that would make sense in federated systems, which we basically haven't got. We have a long way to go in those directions. And of course, I also want to indicate that there are sort of quite big theoretical gaps in doing all of this type of stuff that need to be filled. And the development of empirical best practices, the exact type of things that have happened in the centralized space, where people have worked for so long, now need to happen in the federated one, I believe. And so with that, I'm happy to take a couple of questions. I'm sorry we did run a little bit longer than I expected, so I apologize for that. But yeah, happy to take questions. Thank you for the time today.
Yeah, thank you. It was really nice talk. I think let's take some of the questions. So I see that Nikos posted a question. Nikos, do you want to just unmute yourself and ask a question, or I can read it aloud for Nick?
Okay, hello, thank you.
Yeah.
I just was wondering, because in typical federated learning settings, where you have an exchange of the model parameters between the server and the clients. So this is fine for a small neural net, but I'm wondering how possible is this for a full LLM, which are big models, and can we do that for computation or bandwidth constrained devices like mobile phones, or are we only talking about clients with huge capabilities like data centers or many GPUs?
No, it's a good question. I think it's just the same way typical FL is examined from a cross silo and cross device setting, and those methods are often quite very different. I'd imagine that we will need quite different methods to the ones that we're using right now for it to work with devices. It's just the fact, like you can't even, for the types of devices you're just referring to, you can't even stand up a decent sized model in terms of being able to do a backward pass through it. So there's lots of challenges there, but I do think they're completely surmountable. So I think in time we will have these mobile devices, constrained devices participating, perhaps not fully and perhaps supported by other devices. But I don't think this is an approach that will never work for mobile devices, the same way that, like, literally 6 months ago, 3 months ago, I'm talking to people and they strongly believe that federated learning could never scale to even 1 billion parameters. To also answer your question, there is if you have even in the cross silo setting, there is a considerable amount of data that's being exchanged, but it is completely affordable for training models of this kind. You don't need very fast links. Typical, like, links that you have in your home are fast enough to have those GPUs or those sort of compute participating together, so that the communication speed is not a barrier. The amount of compute needed to sort of participate doesn't appear to be needing necessarily H100s. We've used A100s, our 1 billion parameter. We've done that with A100s. We've done it with A40s. We've done it with mixtures of GPUs. So each of them might have some, even non-trivial types of techniques to kind of balance out different factors to make the system work optimally. But what is really interesting to see is that we get a huge mileage from even just default settings that are quite recognizable. So local optimizers like Atom, and then the outer loop optimizers like Fed average actually in our settings work extremely well. The 7 billion parameter model we showed works. It was done with Fed average. We think, of course, you can move these things forward with more exotic forms and so on, but they're actually not always the key thing driving the system. As you saw with the depth technique, making this a change to the embeddings actually drives a lot bigger performance factors than sort of maybe the choice of the outer optimizer, which in my mind seems to be a bit of a detail.
Great, thanks a lot.
Cool.
I can see another question from Yanis. Yanis, do you want to unmute yourself, or I
Yeah,
can also.
hi. Sorry. So,
Yes.
congrats on the 7 billion parameter achievement. So you mentioned that like the photon framework can be used to recognize the hardware that is present in a data center or something. So you mentioned that it will recognize like the whether GPUs are connected via PCI Express or NVLink, but I assume that you wish to take this a step further and like have that system recognize the entire topology of the training hardware. So how do you plan on getting the devices to like coordinate with regard to like the validation of the model? So like in that setup, how does each device know when to stop the training or which like data to use for that particular training?
Oh, so your question is, so your last question was quite specific. Is how does a node know which data to use?
Yes, but I assume this extends to the fact that you have these distributed data centers, right? And like training
Well, I
a
mean,
model. Sorry.
I mean, it's a bit generous to call them a data center. I mean, the ones we're playing around with today, for example, are just H8 H100s. So I mean, to me, a data center is like, a couple of thousand H100s. These are almost, these are things that academics might have available potentially.
Okay, so how does each data center know when training ends or when like the results are satisfactory?
Oh, I see. I mean, you would just do it as a typical, you can send a signal from the aggregation server when you believe that the perplexity looks fine. So nothing, I don't think there's anything, there are interesting questions in that way, in that direction that you could explore to improve things, but that's the kind of typical approach we're taking. The same way that I think there is some interesting curriculum sort of style thinking that can be done about when you're using certain data from different nodes, or trying to understand the data quality that exists at different nodes. You can be smarter about how you're doing things. But right now, Although we have some work on how do you do federated data quality selection too, but generally speaking, right now we just have a basic system that's trying to train over all the data that's available at each of their nodes. And where well, it actually brings up one thing. I think the one of the real levers we need to pay attention to would be automating as much of this as possible without sort of having manual intervention to do things like data quality assessments, or the construction of batches, or the working out of what embedding needs to be used, which is actually commonly happening now in centralized settings. If people want to have a fantastic set of benchmarks on their LLM, they will come up with very particular types of recipes and ratios and mixtures of various kinds of data to exceed on different downstream tasks. But I think where Federated also can win is by developing methods that are adaptive to these settings, where the manual effort is taken out and we're really leaning more heavily on making more data available for training, rather than sort of carefully crafting data together that I see a lot, that I see happening a lot in centralized. Perhaps that's a little orthogonal to what you're saying. But I guess also you had a question of how do we know about different speeds? It's just some simple probing goes on in terms of the speed that's available. The optimizers might behave a little bit differently if there's different types of hardware available. If you have some small GPUs working with some larger ones.
And just like a quick follow-up,
Sure.
in what happens in the case like of like hospitals where so say I have a global model, looking at the metrics you describe, I'm really satisfied with the way it behaves on a metrics based so I see, like, for example, the loss curve, and it looks that it's converged. So but like, do I actually know its true performance without like testing it on like each individual hospital using its own protected data, right?
Well, I mean, I think in a hospital case, it would be quite reasonable to do something like federated evaluation, where you could do your pre-training in this way. I imagine there must be some task the hospital cares about, so you can do some fine-tuning to shape that model to address a particular task. Maybe it's like summarization of doctor's notes. And then with the same system, you can actually push that model down and have it be tested on the actual private data of the hospital on various locations. And so that would be quite doable under federated learning, and quite reasonable.
Okay, so like, shouldn't what you were talking about, like doing the whole procedure like automatically, right? Automating these procedures. So
Yes.
like, you in this scenario, it would, like, this entire process would be automated, like pre-training, then evaluating on the local, like, protected data sets, because you mentioned about like settings where the data set itself is protected and should remain private. So, and then like the whole procedure going over until like some convergence, because like we may not know the true point of convergence from the pre-training stage, right? Like where the training should end.
Sure. Yeah, there's quite a bit of information about the model quality that does come from testing many different downstream tasks. Typically, I mean, I think when you're training these models, you're not really worrying about one single task, but you're hoping that they'll perform pretty well on a variety of tasks. And so you probably don't give a check mark to that model being great until you've evaluated them on various tasks. And then this is exactly what happens in centralized. It's not really that different to federated. Then you might consider changing up something in that training recipe and so on. And yes, I believe that it is important to have these things as automated as possible, because then I think we can start to have more capable AI models that are not dependent on a bunch of hyperparameters and sort of like a weekly accounted for human labor that is a common sort of thing happening in centralized. I think it's sort of, it's basically like the dark matter of the quality of some of these LLMs is not only how much data they use but it's also how they use that data and the amount of effort it takes to kind of, the sort of magical recipe of like how much math data set do I have with how much language, with how much something else results in a foundation model that has all this sort of nice metrics on the downstream tasks that I can show on Hugging Face leaderboards and so on.
Yeah. Thank you.
Yeah, sure. Thanks for the questions. It's good. Thank you.
I think we're already running quite a bit over time, but I think if you can stay maybe to take 1 or 2 more questions, maybe like a quick
Sure.
ones. Let's see whether somebody from the audience has. I would have maybe one quick one.
Yeah, sure.
So when you scale these models to like 7 billions, even beyond that, what are the techniques that kind of we know that for federated learning they work well for small models and somehow scale seamlessly to these large models? And whether you also have the example of something that we know that works well for small models, but for some reason doesn't scale up well when you try to apply it to the large models.
That's a good question. What have we found in that case? Things that don't work that well. Yeah, I guess we haven't tried enough of these different techniques that the community has come up with yet, because each run is sort of expensive. So we haven't done a big sweep over different methods. I'm trying to think if there's anything that stood out that we observed that was not working that well. Nothing jumps to mind. Certainly the embeddings. So that's not a federated technique, but just using the embeddings off the shelf, where it was not a good choice and actually led to like the calculation of loss being incorrect in some cases, because because normally you get a chance to shape that data well and you know what's there, but now you have an individual client with a generic embedding where where it might not be representative for that data at all. Yeah.
Okay, yeah, thank you. And maybe another one related to this question. So in terms of scaling these models up and make training very like essentially they work almost the same way as in a centralized training, what do you think are the promising research direction where we kind of among or promising challenges to look at among the ones that you listed that you consider uh, the ones that would be the most impactful for scaling up the models?
For scaling up the models, I think being able to have I'm not going to get a perfect list here, but something that jumps to mind is I think it's important to have the ability of these systems to work well even when some nodes stop participating. And so I think it's because we even see that in data center settings, and it's something that we've built into the system from day one, where we wanted to have it possible that the same way in a federated setting that a node might just stop participating from one round to the next. But we still wanted to have the model converge well. For example, we have the optimizer settings not carry over between the rounds and so forth, which is an important aspect. And I think that is so building that robustness into these systems is important, because the amount of work that they're doing and the amount of communication being exchanged, you really don't want to lose that. I think also if you look at the full chain of what people do centrally, it's sort of what I was alluding to before. There's a lot of things that they're doing that are based on being able to look at the data and to kind of iterate over the mixtures of the data, sort of tuning hyperparameters and so on. That is not easy to do in federated settings. Obviously, you can always do sort of grid search of parameters and so on. But over time in centralized, we've come up with nice heuristics that work pretty well. We sort of really don't have any of that for federated. And although I think And that's going to be critical in us being able to convince people that these models are worthwhile, this approach is worthwhile pursuing and persisting with. Because there will be definitely a comparison game of downstream tasks. Now, in some sense, centralized, and actually not in a very real sense, centralized is this huge advantage because you have a huge amount of people trying all these tricks, ranging from very small tricks to very big tricks, trying to find ways to juice those numbers. And on the federated side, we might lag quite heavily in different cases, particularly for different downstream tasks. And that might only be because we haven't had sort of the exhaustive search of these tricks. And in some sense, it's almost like grid search by volume of community. And so I think that's going to be an interesting factor that comes top of mind. Maybe it doesn't end up being the most important research problem, but it's something I worry about. And then I also expect that there is a fairly big umbrella of low-hanging fruit techniques to be discovered the same way, and as LLMs started to be really important to train and the performance of these models are really important, then there's been a lot of interesting tricks come up, such as like flash attention. And now, flash attention is this default thing everyone uses. It's a really interesting idea. It's great that they developed it, but it's not, it wasn't like the internal composition of that technique is not sort of a huge jump. You can kind of see where that can make sense, and it's a very pragmatic, good, excellent technique. So I'd imagine there's going to be 3, 4, 5 techniques at least that people can discover for themselves related to all across the stack, I think, of the federated system of how you select data, how do you maybe break down the models in some different way. I think probably things like PIFT might have a role to play, where you can have participation of different clients, and even just the hyperparameters. How many clients do you want to have involved? How many are needed to get a good sense of the direction of the model? All these things I think can be revisited. It's just that I think you asked, your first question here was spot on, but I think we don't have the answers yet as to what will not work just yet. But I'd encourage everyone to take a look, and I think even you can start to get sense of this at even the 100 million parameter range. That might be a bit more easy to train as well.
Yeah, thank you. And thank you for sharing your presentation also.